Section 21.4 Rates of Radioactive Decay. Such radioisotopes, such as uranium-238, are found in nature, although they're not stable. Other radioisotopes do not exist in nature, even though they can be synthesized in nuclear reactions. To understand this distinction, we must analyze the different nuclei undergo radioactive decay at different rates. Many radioactive isotopes decay essentially completely in a matter of seconds or less, so we don't find them in nature. Uranium-238, on the other hand, decays very slowly. Therefore, despite its instability, we can still observe what remains from its formation in the early history of the universe. Radioactive decay is a first-order kinetic process. Recall that first-order processes has a characteristic half-life, in which the time required for half of the given quantity of substance to react. The rates of decay of nuclei are commonly expressed in terms of their half-lives. Each isotope has its own characteristic half-life. For example, the half-life of strontium-90 is 28.8 years. If we started with 10 grams of strontium-90, only 5 grams of that isotope would remain after 28.8 years. 2.5 would remain after another 28.8 years, and so on. Strontium-90 decays into yttrium-90. The loss of strontium-90 is a function of time, as shown in Figure 21.8. Half-lives are as short as milliseconds of millionths of a second and as long as billions of years are known. Half-lives of some radioisotopes are listed in Table 21.4. One important feature of half-lives for nuclear decay is that they're unaffected by external conditions such as temperature, pressure, or state of chemical combination. Unlike toxic chemicals, therefore, radioactive atoms cannot be rendered harmless by chemical reaction or by any other practical treatment. At this point, we can do nothing but allow these nuclei to lose radioactivity at their characteristic rates. In the meantime, we must take precautions to prevent radioactive isotopes, such as those produced in nuclear power plants, from entering the environment because of the damage radiation can cause. Radiometric dating. Because the half-life of any particular nuclide is constant, the half-life can serve as a nuclear clock to determine the ages of different objects. The method of dating objects based on their isotopes and the isotope's abundance is called radiometric dating. Carbon-14, for example, has been used to determine the age of organic materials. This technique is known as radiocarbon dating. The procedure is based on the formation of carbon-14 by the capture of solar neutrons in the upper atmosphere. This reaction provides a small but reasonably constant source of carbon-14. The carbon-14 is radioactive, undergoing beta decay within a half-life of 5,715 years. The carbon-14 is incorporated into carbon dioxide, which is in turn incorporated through photosynthesis into more complex carbon-containing molecules within plants. When animals eat the plants, the carbon-14 becomes incorporated within them. Because a living plant or animal has a constant intake of carbon compounds, it's able to maintain a ratio of carbon-14 to carbon-12 that's nearly identical to that of the atmosphere. Once the organism dies, however, it's no longer ingests carbon compounds to replenish that carbon-14 that is lost in radioactive decay. The ratio of carbon-14 to carbon-12 therefore decreases. By measuring this ratio and comparing to that of the atmosphere, we can estimate the age of an object. For example, the ratio diminishes to half that of the atmosphere. We can conclude that the object is one half-life, or 5,715 years old. This method cannot be used to date objects older than 50,000 years. After this length of time, the radioactivity is too low to be measured accurately. In radiocarbon dating, a reasonable assumption is that the ratio of carbon-14 to carbon-12 in the atmosphere has been relatively constant for the past 50,000 years. However, because variations in solar activity control the amount of carbon-14 produced in the atmosphere, the carbon-14-carbon-12 ratio can fluctuate. We can correct for this effect by using other kinds of data. Recently, scientists have compared carbon-14 data with data from tree rings, corals, lake sediments, ice cores, and other natural sources to correct variations in the carbon-14 clock back to 26,000 years. Other isotopes can similarly be used to date the types of other types of objects. For example, it takes 4.5 times 10 to the 9 years for half the sample of uranium-238 to decay to lead-206. The age of rocks containing uranium, therefore, can be determined by measuring the ratio of lead-206 to uranium-238. If lead-206 had somehow been incorporated into the rock by normal chemical processes instead of by radioactive decay, the rock would also contain large amounts of more abundant isotope lead-208. In the absence of large amounts of this geonormal isotopes of lead, it's assumed that all the lead-206 was at one time uranium-238. The oldest rocks on Earth are approximately 3 × 10⁹ years old. This indicates that the Earth's crust has been solid for at least this length of time. Scientists estimate that it required 1 × 10 or a billion to 1.5 billion years for the Earth to cool and its surface to become solid, making the Earth 4 to 4.5 billion years old. Blech. Calculations based on half-life. So far, our discussion has been mainly qualitative. We now consider the topic of half-lives from a more quantitative point of view. This approach enables us to answer questions of the following types. How do we determine the half-life of uranium-238? Similarly, how do we quantitatively determine the age of an object? Radioactive decay is a first-order kinetic process. Its rate, therefore, is proportional to the number of radioactive nuclei in the sample. The rate order constant K is called the decay constant. The rate at which a sample decays is called its activity, and it's often expressed as the number of disintegrations observed per unit of time. The becquerel is the SI unit for expressing the activity of a particular radiation source, that is, the rate at which nuclear disintegrations are occurring. A becquerel is defined as 1 nuclear disintegration per second. An older but still widely used activity is the Curie, defined by 3.7 × 10⁻10 disintegrations per second, which is the rate of decay of 1 gram of radium. Thus, a 4 millicurie sample of cobalt-60 undergoes 1.5 × 10⁸ disintegrations per second, has an activity of 1.5 × 10⁸ becquerels. As a radioactive sample decays, the amount of radiation emanating from that sample decays as well. For example, the half-life of cobalt-60 is 5.26 years. The 4 millicurie sample of cobalt-60 would, after 5.26 years, have a radioactive activity of 2 millicuries, or 7.5 × 10⁷ becquerels. As we saw in section 14.4, the first-order rate can be transformed into the following equation. The natural log of n to the t over n to the o equals negative kt. In this equation is the time interval of decay. K is the decay constant. N sub naught is the initial number of nuclei, and n sub t is the number remaining after the time interval. Both mass of the particular radioisotope and its activity are proportional to the number of radioactive nuclei. Thus, either the ratio of the mass at any time t to the mass of time 0, or the ratio of activities of time t and time 0 can be substituted for n sub t over n sub o. From the equation 2119, we can obtain the relationship between the decay constant and the half-life, t sub 1/2. So K equals 0.693 over t sub 1/2. Thus, if we know the value of either decay constant over half-life, we can calculate the value of the other.